Hello all, welcome back. So today we are starting lecture 13, and today and the next lecture, lecture 13 and 14 will be our concluding lectures on the two terminal negative resistance devices for microwave oscillation primarily. So we will be discussing about tunnel diodes and then about Gunn diodes, and we will see how they work, the physics of their working, how commercial devices look like in this category, and how they are used for microwave oscillation. Okay. So over to the whiteboard here. So first thing we will talk about is tunnel diode, and after tunnel diode we will talk about Gunn diode. Okay. So the name, as the name suggests, tunnel diode, it basically uses the quantum mechanical process of tunneling to get a negative differential resistance, NDR. So if you recall, in our impact diode we talked about a negative differential resistance in the AC signal, where the current and the voltage are out of phase. You remember we had a phase difference of around 180 degree, and because the current and voltages are out of phase, we call that an AC negative resistance, and we use that to generate oscillation. We use that to generate an oscillation, and impact diode was used for an RF oscillator, and you need a cavity or kind of a tuning circuit where you place it such that you can sustain the oscillation. Okay. So that was in the AC. However, a tunnel diode can give you a negative resistance even in the DC. So when I say negative resistance, it means the current decreases with an increase in voltage which is opposite to what you would typically achieve. So in a tunnel diode, if you plot the current versus the voltage, okay, the current will first rise, then it will fall, and then it will rise again. Okay. It is very interesting because this part is where we call it, the diode exhibits a negative differential resistance, because you can see that the current is actually decreasing with an increase in voltage. So the slope of this is negative, right, it is negative. So this negative slope, or the fact that you have a negative resistance here, in a way is exploited to generate microwave oscillation. Okay. It is used to generate microwave oscillation. However, tunnel diodes are not commercially as successful as, for instance, Gunn diode or impact diodes. Gunn and impact diodes are still used actually for generating RF or microwave signal of sufficiently high power, and they have their own advantages, but tunnel diodes are not so much commercially successful because of different issues, such as the power level would not be as high. Okay. And Gunn and impact are more mature technology, they have been exploited for a really long time, they are really out there in the market, and strategic sector also uses them. But nevertheless, the tunnel diode is a good concept, it is a good physics concept to understand and to see how it generates a microwave oscillation. So the way you get this kind of a device IV, or the characteristic, is that you use a very highly doped, for instance, p-type material and a very highly doped n-type material. Okay. A p-n junction where you have very highly doped materials on both sides. In that case, what will happen, you can expect to see a tunnel diode. How does it work? So essentially what happens is that if you have a very highly doped p-type layer, or if you have a very highly doped n-type layer, so if you recall, if you have a very highly doped n-type layer, so how will the band diagram look like? You have EC, you have EV, and the Fermi level will be almost at the conduction band, or it could be even above the conduction band. Similarly, if you have a p-type material which is very highly doped, so this is your valence band, the p-type, the Fermi level could be below the valence band. Okay. So if you join them together, the p-type and an n-type material, what is the kind of band diagram that they will form? Okay. So the kind of band diagram that they will form is that, of course, there will be very little depletion because they are very highly doped. So you have a band that looks like that, this is your conduction band. Okay. And your valence band will be something like this. Okay. This is very narrow, this depletion or this band bending that happens is in a very narrow region. Okay. And for instance, your Fermi level will be up here, okay, because it is very highly n-type dope, and in equilibrium the Fermi level is the same everywhere. So this Fermi level is also here. Okay. So it is in equilibrium, and this is at V equal to 0. So the applied voltage is 0, and this is an equilibrium condition. So what you can say is that the Fermi level is aligned, and this is how the band diagram looks like. Now the moment you apply a small bias, okay, the moment you apply, for instance, a small forward bias, say 0.1 volt, okay, a small forward bias, this is your p type, this is your n type. So if you apply small forward bias, then this you push down, this you push up, that is how it works. So the electrons that are here, and there are plenty of electrons, they can actually tunnel, this barrier is very thin because it is very highly doped, they can actually tunnel here and go into this part is an empty state, you can say. You need electrons or holes to tunnel, and on the other side of the barrier you need some empty states to tunnel to. So, this is an empty state where it means it is actually electrons can come here and recombine with holes, essentially that is what it means. Okay. It can come and recombine with holes, and that gives you a current. So, that current actually is the current that I had drawn. This is your I and this is your V. So, initially it goes like that, correct. So, this part, you know, the initial increasing the current is increasing in this part, right. This part corresponds to the tunneling current. This is tunneling. Okay, it keeps tunneling. However, as you keep applying more and more voltage, say you go to plus 0.5 and plus maybe 1 volt depending on the material you are using, what will happen is that your band will gradually start looking like this. So, the band bending will decrease because you are applying a forward bias, right. So, you have this Fermi level F here and the Fermi level F here. Now, the electrons here will find it difficult to tunnel because this is a forbidden gap, the band gap is forbidden gap. So, there is no empty states here, okay. There is no empty states to tunnel to. So, what it means is that the electrons now will find it difficult to tunnel because there is no empty states here. So, the tunneling current will drop because you initially this was, you know, it was like that where there is enough tunneling state, but gradually the tunneling because you are applying a forward bias, so the band bending is happening. So, now the Fermi level is aligned to the band gap, you know, the forbidden gap. So, electrons cannot tunnel, and so the current will drop, the current will keep dropping. Okay. Now, what happens after that, right? One second. Okay. Okay. So, what happens after that? So, now you have something like that where your Fermi level is here and the Fermi level is here, and it cannot tunnel, it cannot tunnel. So, the current will drop, correct. So, the current rises and then drops. However, eventually the thermionic emission, you know, like the normal drift diffusion that is characteristic of any p-n junction will start. The normal drift diffusion where the electrons from the n side are injected to the other side, the holes from this side are injected to the other side. So, that the normal p-n junction transport will start happening, and so the current will start rising again like that. Okay. So, this part is the normal drift diffusion limited or the normal p-n junction. Okay. This part is the tunnel, and this part is when the tunneling current is dropping. Okay. So, this is called the valley and this is called the peak. An important parameter is the peak to valley ratio. Okay. PV, this peak to valley ratio is a very important parameter, like how much peak getting, how much valley you are getting, and this is your negative differential resistance. Anytime you have a negative resistance like that and the value is not negative, it is just that with increasing voltage you have a decreasing current. This negative voltage can be used to create an oscillation, because okay, you can create an oscillation. In a way you can say that anytime you have a resistance R, and if you have a current that is flowing, you have an R square R loss. But if your current is, if your resistance is negative, then your R square R, okay, this is actually not loss, it is generation. So, you are generating power in a way, okay, you are generating power in a way, and in this case you can actually get a microwave power out of it. That is why you are generating microwave. Okay. So, now before I go to the microwave generation, of course, what is very important here is to see that if you have a IV characteristics like the one I told you, something like that, then when you want to generate microwave, for instance, or when you want to the device to oscillate, where can you bias the, you have to bias the device somewhere, right. So, one of the thing is that you can bias the device at any point, suppose a point A here. If you bias the point such that you have a load line going like that, load line is that, you know, the line in an IV characteristics where you are biasing the device with the resistance that you are putting in. So, the device will oscillate around this point, but this point is a regular IV, you know, the current is increasing with respect to voltage. So, you are not going to get any microwave oscillation. We call it like a monostable point, monostable bias point, you know, because you are not explicitly getting anything out on microwave here. Now, this point is suppose B, and you know, this point is suppose C. So, if you okay, so if you bias at the point C along a load lines which goes something like this, okay. Then this is a bistable, okay. If you say bias at a point B, suppose you bias at this point B, but your load line is looking like that, then the device will actually go either to the point A or point C, it will not remain at point B, it is called bistable, it will try to get this point or this point, you will not get microwave oscillation. So the way to actually bias the device to get microwave oscillation would be to bias it in a point such as B, where you have a load line that looks like this. This is your load line and this is your A stable point, okay. So you want to bias the device at this point B in a load line that looks like this, okay. In that case you are going to get a negative resistance Rn, for instance, okay. That is your negative resistance of the diode, okay. And what happens is that your the slope of this minus di by dV at this point of B is your actually minus 1 by Rn, the resistance, the inverse of the resistance, okay. So that is your circuit behavior. Now if you want to look at a circuit representation of this diode, of this tunnel diode, then the tunnel diode has a negative resistance, so that is minus Rn, and then because it is a PN diode, there will always be a junction capacitance in parallel, okay, and this junction capacitance can be captured by something like say C, okay, which is in parallel. This junction capacitance actually is measured at the valley, you know, at this point you measure the junction capacitance, and then of course the package might have its own, or the contacts, the package, the parasitics can have their own resistances, and then they can have their own inductance like Ls, right, that could come from, yeah, as I told you, from different parasitic components like such a package. And looking inward you have the input impedance of this circuit, okay. So people can find out the input impedance based on this RLC, you know, parameters, and you can actually express the input impedance as a function of these parameters RS, LS. For instance, it will look like something like minus RS minus Rn divided by 1 plus omega Rn C, okay, whole square. This is your real part, and then you will have this imaginary part something something, okay, which I am not writing here. So you can express the input impedance in such a form, okay. You can express the input impedance in such a form. Now the thing is, this tunnel diode can be connected either in series or in parallel with a load, okay, and then you can expect it to behave like a voltage oscillator, or you can expect it to sometimes behave as a voltage amplifier depending on the biasing condition. For instance, if I go to this circuit again and you have a minus Rn and you have this capacitance here, right, and then you are going to connect it in parallel, for instance, across a load, okay. You want to connect it across a load which is your RL. This is the load across which you are delivering the RF power, for instance, and this is your tunnel diode, correct. This is your tunnel diode, and then you will have to have some voltage source, correct, some voltage source you are giving, and the voltage source will have its own voltage resistance, say Rg, correct. So what happens is that in this case you can actually define the gain of this circuit, you know, the gain of the circuit A, and there is a simple math with a Kirchhoff's law that you can define, and it comes out to be something like Rn, the value of this resistance, Rn minus Rl, okay. It comes out to be something like that. So essentially if you can choose your Rn to be approximately equal to Rl, then this quantity will go to infinity and the system will start oscillating. The system will start oscillating, okay. So this oscillation frequency will of course be determined by this the circuit components and parasitics and other things also, but you can connect this also in series, by the way. You can connect this in series, you can connect this in parallel. For instance, in series connection you will have a load like that, and then you have your capacitance, and then you have your negative resistance, okay. You are biasing it at that point, as I told you, right. So this is your series connection, and that is your parallel connection of the tunnel diode across the load on which you are delivering the power. Similarly in the series connection also you have a gain which is A, 1 by 1 minus Rn by Rl, okay. Again if your Rn by Rl goes to 1, then this becomes infinity and the system will start oscillating, okay. But when you go to higher frequency, tens of or hundreds of gigahertz you are looking at, for instance, in oscillation, then your package parasitics can significantly limit the power, and also the voltage swing, you know, if you recall the swing of the voltage across this point, you have to have on this negative curve, right. The voltage swing around that point is actually the swing is quite low, because this is quite low. Because of this low swing, the low voltage swing that you have, the RF power that you can get is also quite low, and that is why they are not very commercially successful, in the sense that your voltage swing is low, and so your RF power that you can get is very low. To compensate for the low voltage, you can have very high large area diode, so that the current is high, the current can be very high to offset for the very low voltage swing. But if you have to have very high current, then your device has to be very large, a lot of large pads, and so your parasitics will again increase. So it is not a very good design that way. Okay, more capacitance will come into picture. So tunnel diodes have not been, that is why very largely successful with respect to commercial application. It can generate some RF power but very low, and it is good for academic research. There is a lot of work going on in, for instance, gallium nitride resonant tunneling diodes, because there people expect that this voltage swing could be large in a wide bandgap or an ultra wide bandgap material. So AL and GaN, for instance, tunnel diodes are it is an active research area that is being pursued. Okay. So I think that was all about tunnel diodes, and now we will come to Gunn diode, because Gunn diode has been more commercially very successful compared to tunnel diode, and Gunn diodes are useful today for generating a good amount of RF power. Okay, RF power right from microwave to millimeter wave. So what is a Gunn diode actually? Okay, what is a Gunn diode? Gunn diode is a little bit more complicated to understand, but nevertheless we will not go into the great details of a Gunn diode, because the exact physics and the operation of Gunn diode can be very lengthy, and it could be a full semester course in the if you just want to talk about Gunn diode. So here we will skim through the basics about how the Gunn diode works and what is the principle, what kind of applications it is looking for, and so on and so forth. So Gunn diode historically have been only certain materials can exhibit Gunn diode behavior, by the way, and historically it was gallium arsenide and then indium phosphide, and then the other materials such as cadmium telluride, for instance, not so widely used, are used for Gunn diode. Gallium arsenide is the most widely used, indium phosphide is also used. So what is Gunn diode? So the Gunn diode also exhibits an IV curve which looks like that of a tunnel diode, you can get something like that. But the phenomena here is very different, and it is actually not a diode, because there is no junction per se, it is a bulk material, it is a bulk phenomena, there is no PN junction, okay, there is no Schottky junction or PN junction, it is just a bulk process. There is no junction, it is a bulk process. Okay. When I say bulk, it is like the bulk of the semiconductor that exhibits this, and it is little bit more physicsy, in the sense that what happens is that this drop in the current that happens, this negative differential resistance that happens, this drop in the current happens because the electrons go from one valley to another valley in the K space. Now if you recall your basics of semiconductor devices, you will recall that we talk about an EK diagram. Okay, we talk about an EK diagram. So something like you have, this is energy, okay, this is energy, and this direction is the K, the wave vector, you say, okay, momentum you can say. So this is the conduction band, this is the valence band, if you recall, okay, and electrons are here, of course, at the bottom of the conduction band. The curvature of this determines the effective mass of electron. The mass of an electron is different in different material, because we call it effective mass. It basically takes into account all the quantum mechanics, all the band structure of the material, and so the curvature, if you have a curvature like that, you have an effective mass of m, for instance, you have a curvature like that, it has a very very high curvature, so your effective mass will be extremely low. Okay. If your curvature is something like that, the curvature is super low, correct, the curvature is super low, so effective mass will be super high, okay, will be super high. Effective mass is typically correlated with the electron mobility, because the electron mobility is given by is directly proportional to effective mass, the inversely proportional to effective mass, okay, q tau by m. Tau is the scattering time, overall the mean, you can say momentum relaxation time, mass, effective mass. So mobility is inversely proportional to 1 by m. So if your effective mass is really low, then your electron mobility will be very high. If your effective mass is really high, then your electron mobility will be very low. Okay. Not talking about holes here, because microwave devices are predominantly unipolar in the sense, or bipolar in the sense that we use electrons, predominantly electrons to transport, okay, especially in 3-5 material like gallium arsenide, MESFET, HEMT, etc. We do not have a hole transport as an active layer, so we are talking about electrons here. And so what happens is that in a material such as gallium arsenide, you take this, you exploit this property of this physics of electron mass being different in different values of material, and because of the effective mass being very different, your electron mobilities can be very different, and if your electron mobilities can be different, then when your electrons jump from one valley to another valley, suddenly the mobility might change, and this sudden change of the mobility, which is happening due to a sudden change in the effective mass of electron, will give rise to a sudden decrease or increase of current. That is the basic principle of the Gunn diode, and this phenomena of this negative differential resistance that comes about in terms of the electrons jumping from one valley to another valley at sufficiently high field is the reason for microwave oscillation. But again, in this case it is a little bit more complicated than a tunnel diode, because there is something else in between the negative differential resistance that you get because of the valley, the different valleys, and the microwave generation. There is something else in between, and that is called a domain formation for gallium oxide, okay, gallium arsenide. So, if to talk about domain formation, of course in the next lecture, but here I just want to show you that using the different values of gallium arsenide, you are able to generate a negative resistance, and that is the physics of this material. For instance, in gallium arsenide, okay, in a gallium arsenide system, you will have something like, for instance, a conduction band value like that, correct, a conduction band value is like that, and then this is your say gamma point, the k equal to 0 point, but then there is another value which looks like this, for instance, okay. This could be another point called say L, okay, another point, this is x axis is k. So, this has a high curvature, so the effective mass is this is actually this the curvature of the, so the mobility here in this valley is actually low, the mobility in this valley is actually low, which means the curvature is high. So, I had drawn it incorrectly. So, essentially what will happen is that you have a valley like that, okay, and then if you remember, if you have a very high curvature like that, your mobility will be very high, correct, your mobility will be very high, and if you have a curvature which is very low, if your curvature is very low, then your effective mass will be very high, and that is why your mobility will be very low. So, essentially what happens is that this is correct actually. So, you have a low curvature here, you have a low curvature here, and you have a high curvature here. So, the low curvature gives you high effective mass, and high effective mass gives you low mobility, whereas high curvature gives you a low effective mass, which is the reason you get a high effective mobility, high mobility. So, initially electrons are all here in this bottom of this band, in this valley, this is the L valley, the primary valley, okay. This separation in energy of between these two is some quantity 0.1, 0.2 electron volt, etc., for instance, and so it will not go from here to there in the other valley in general, but if your applied electric field is above a certain threshold, that means you are supplying sufficiently high voltage or electric field, then electrons will get sufficient energy to go to the other valley, and the moment they go to the other valley, not all of them, they will gradually start going, they go to the other valley, they suddenly see a very low effective mass, because they go into this valley of high curvature, and because of the low effective mass, actually you have a very high effective mass, because your curvature is very low, your curvature is very low here, and that is why suddenly as the electrons go from here to here, the electrons will suddenly see a very high effective mass, a very high effective mass, and because they see a suddenly very high effective mass, their mobility suddenly drops, becomes low. So, what happens is that initially electrons are all in the gamma valley only, at certain high electric field they will start going to the other valley, and suddenly in that valley they will experience a low mobility, because the effective mass is high because of the low curvature. So, because the mobility suddenly drops, what happens is that your current will also suddenly drop. So, you had a current, you had a voltage, the voltage is the same as the electric field, by the way. So, you can plot field here. So, the field initially you will get current, because only this is participating, okay, this is participating here, but at one point when electrons start going to the other valley, the current will start decreasing, because this part is where suddenly the mobility has become low, okay, suddenly the mobility has become low, and eventually you will again rise it here, okay, because you will go to equilibrium, not equilibrium in a steady state, where you are now putting in sufficiently high electric field. So, these electrons will basically, the electrons in the other higher valley, this is a higher valley by the way, higher valley will start conducting nevertheless, because although the mobility has become low but the carrier density is increasing anyways, so you will get a high current here, okay, and that is the reason why you get a negative differential resistance in a Gunn diode. And you use this principle to actually generate microwave oscillation, and how you do that we will see that in the next class, okay. So this is the end of today's lecture, where we basically talked about tunnel diode. We discussed about how the tunneling diode works and how you generate microwave, and at the same time we introduced about Gunn diode and the principle of working of the Gunn diode, that it has two different values, certain materials. So not all materials can exhibit Gunn oscillation. You cannot expect silicon or germanium to do that, but gallium arsenide can be used to do that, because its EK structure allows for electrons to be transported from one valley to another valley of different curvatures, which is to your advantage, and using that you can suddenly experience a negative differential resistance, which is why you get an IV curve, or a voltage or electric current density and electric field curve which exhibits a negative differential resistance, okay. So with that we will conclude this lecture, lecture 13, and we will continue from where we left today in lecture 14, and we will wind up this discussion on Gunn diode, so that from lecture 15, which is next week, we can start on 3-5 devices, MESFETs, okay. Thank you.